Holy shit.
Yeah, so
Did you almost, what happened?
I almost laughed how woefully unprepared I was because there was a guy I went up against. My main event is the 500. He coasted the whole time and blew my fastest time out of the water.
Oh no.
Without even trying.
Oh no. Where's this guy from?
Oh,
Oh, okay.
Gotcha.
I got it.
I was not even ready for that. Like, I did league finals last year. My 500 was the fastest in our league. And then this guy comes along.
There's always somebody. There's always somebody. All right, guys. If there's no questions from the test or leftover from homework stuff, we're going to get right into chapter 3, which some of you guys will really love because we're going to officially learn shortcuts. Right? Oh, yeah. Because, good Lord, we know we don't want to use the definition of derivative for everything. In fact, some things it's basically impossible. So we need to start noticing patterns, making shortcuts, and then building on those shortcuts. Is what we're going to be doing. So the very first thing I want to look at. So for example, let's do this first. Let me introduce some notation. Let me figure out where I want to be. I think I want to be here. So we already know if I'm given this, we know this. Right? But so what is this? The prime is how you read it. What is it? The derivative, the slope, 11. 11. So derivative is slope, kick ass. So what would this be?
Slope.
Yeah, it'd be the slope of the slope. Now, I really want this to make complete sense. When you take a derivative, isn't this a function in its own right? Isn't that a function? And what can you do with any function? Take its derivative, right? Or not any, but you know what I'm saying. You guys good? So of course, this could keep going, and we go up to 3, but then it starts to get a little insane, right? So then we just start putting a little number in a parenthesis after that. So, for example, if this was position, remember position is S. What's the first derivative?
F
prime, which would be what? What do we call it? If this is position, the rate of change of position over time is
Velocity.
velocity. Like, I was going to start doing sounds like. And of course, rate of change of velocity is your acceleration. Does anyone know what this one would be?
Light speed.
Say again?
Light speed.
All right, is everybody with me so far? This is nothing huge, nothing groundbreaking.
So we're never going to get to that point in this course?
Say again?
So we're not going to go beyond like the final prime?
Oh, hell yeah. Remember, so we could, you're going to see problems that's this. What does this mean? Any derivative, right? So there will be problems in your homework where they give you a function and they ask you to figure out what any derivative is. So we're going to work up our way there. Okay. As far as equations of motion, we normally only do the first 3. The next one does have, well, they all have physical meaning, but the next one is something. You ever had a car that you push on the accelerator and it goes like, okay, maybe I'm gonna go now. What is that in motion? What are we? Jerking. Jerking. This is the jerk. So the jerk is how your acceleration changes. And if you had a shitty car like I did, my very first car, right? It got me places. That's all that matters.
So wait, velocity and acceleration.
No, careful. What's this? Position. Right? Of course we use a letter S for position. Because we're weird ass math people. Derivative of that is velocity. So the rate of change of position is velocity, rate of change of velocity is acceleration, rate of change of acceleration is jerk. Now this one is not something we think of every day, but it's kind of cool that we actually call it what it basically is. Anyway, all right, so that's beside the point. So I just wanted to make sure you saw this notation, you know what it means. it definitely does not mean this. What does this mean?
Inverse.
Good. Which is not this, yes? That does not mean reciprocal, it means inverse. What if I wanted the reciprocal? What if I wanted this to be the answer? What would this look like? It would look like that. There we go. Now that means reciprocal. All right. I like it. And again, math is a different language. It just is. So like any different language, you have to learn the grammar. This is part of the grammar. Right? Grammar is how you can put things together to make sense out of them. This is the grammar of math. Maybe there. All right, so what about, all right, let's go back. What's the limit definition? I'm going to use a different marker. You're kind of dying a little bit. Limit definition of derivative. What's the limit definition? I'll put the limit here.
Limit
As x approaches a.
of h.
There we go. This is the definition of derivative. There's another way to get the derivative. This is an alternate method. But when we say definition of derivative, we mean this. Yeah. And what goes up?
F of x plus h minus f of x divided by h.
Good. And it's just y2 minus y1 over x2 minus x1. Okay. Never forget that. We're going to do some funky things with derivatives. Never forget it's just the slope of some function. That's all it is. Sort of like trigonometry is just ratios of sides of triangles. Yes? You guys agree with me on that? That's all trig is ratios of sides of right triangles. Of course, do we do a lot of shit with it? Yes, more than you wanted, right? Okay, now watch. This is going to get interesting. Let me see. I don't want to do this. What order? Yeah, okay, let's do this. I think we've done this once before, but let's do this. What if I had f of x, example, is x cubed? Right? So let's do this together just to kind of make this quick. Well, we'll go in here.
X plus h cubed.
X plus h cubed minus x cubed f of x, right? Come up all over h. Now I know I showed you, didn't I show you guys kind of a shortcut to this? And let me be a little more precise with this, because it's going to lead right into our next thing. Pascal's triangle. This looks like somebody was just bored, right? And they're like, all right, let me just make a little pyramid. And you can keep going. What's the pattern? What would go here? One. What would go here? 5. 1 plus 3 is 4, 3 plus 3 is 6, 2 plus 1 is 3, 1 plus 4 is 5. 10, 10, 5. Okay. You guys see that? And that's just somebody playing with numbers because they're bored, right? Well, actually, this is insane. This is insane. Let me do this the quick way, and then we'll verify it. So here's the quick way to do this. 0, 1, 2, 3. The third row here, right? This is so cool, right? And let me see if I can do a little bit. I don't know what you're gonna look like. Wouldn't if I wrote this 3 times, wouldn't one of my things be x cubed, like all the x times x times x, right? I do not recommend you do this way, but wouldn't I get an x cubed out of this? And then wouldn't I get an x times h a few times, x squared h's, right? So here's how this is so cool. So this will be, so I'm on this level here, right? on that level there. Oh shit. Oh
Sorry,
shit.
trying to move your camera.
Thank you. Yeah, I need to figure out how to see more, but still be able to see everything. Yeah. Okay, now watch this. This is so cool. So I got 1, and then I start off with all x's. That captures the x times x times x. And then I can do x times x times h, or x times h, or x times h. So I get 3 of them, right? 3 x squared h. So 1 all x's plus 3, 1 less x, 1 more h, plus 3, 1 less x, 1 more h, plus 1, get out of there, h cubed. I love this idea. So the Pascal's triangle tells you the coefficients, and then you start all of one, none of the other one, decrease, increase, decrease, increase, decrease, increase. So I could do x plus h to the 11th relatively quickly. I would just have to take this out to the 11th row, and then I can put it together. Okay, I don't know if you guys agree. So watch this. What is x plus h times x plus h?
X squared plus
2xh.
Yeah, 2xh
plus 8.
squared. What's the coefficients?
1, 2,
1, 2, 1. Right? All x's, 1 less x, 1 more h, 1 less x, 1 more h. What do I get if I multiply this by x plus h? I get x cubed plus 2x squared h plus xx squared plus hx squared plus 2xh squared plus frickin' h frickin' cubed. 2x squared h plus hx squared is 3x3, right? And then h squared, good lord, my job is hard if you can't speak. Hx squared plus, I'm sorry, where? Xh squared plus 2xh squared is 3xh squared. You've got the same damn thing. Yes? Yes? So it's really just a bunch of, if I have 3 things, how many ways could I pick 2 of them at a time? That kind of thing. Okay. Crazy shit. All right, let's keep going with this. That's going to come back in a minute. So that's this, yes? That's this, minus x cubed over h. And of course, what happens there?
the x cubes cancel out.
X cubes cancel. So I get 3, let me go ahead and kill the h's at the same time. Is that cool? 3x squared plus 3xh plus h squared. And then of course, if you let h go to 0, that's just
3x squared.
3x squared. What's it look like happened from the beginning? Where is my thing? Here it is. To get to there, it looks like the 3 just kind of came down, and then the power went down by 1. And that kind of jives with what we were seeing visually, right? When we started with a 4th power, the slope that we did came out to look like a cube, right? I like it. I know some of you guys know this already because you tried to use it too early. Now we officially are starting to know some of these shortcuts. So you will be able to use them. Now, oh man, this board sucks bad. All right. This board sucks bad. Okay. So let's do this one. What if f of x was x to the n? This sounds exciting, yes.
Well, then you bring h down, right, and then you do h minus 1.
N. But I'm with you.
Or, I mean, n minus
We have to prove that. We don't know. All we know so far is that it looks like that's what happened. Maybe that's not really the rule. Maybe the rule is it's always 3 times x and the power goes down by 1. Maybe that's the rule. I don't know. We only got one thing to go on here. It's not enough. So we're going to do every single possible power all at once. Does that sound exciting? All right. So if we set this up, what's it gonna look like? Goes here.
X plus H to the power of n.
That looks yummy. Let me make sure that's an n. Minus x to the n, right?
Mhm.
Now watch this. We're gonna kind of hand wave this away. There's more to this than there's like, if you've ever taken statistics, you might have heard of combinations, combinatorics. We're not gonna do that,
Okay.
right? Don't worry. But let me kind of do this well enough. If I do this, whatever, I'm on the nth row of that triangle, yes? Okay. But what's the first coefficient going to be? Always. 1. I'm going to have 1, nothing but x's, yes? Because you start off with every x and none of the h's. So I'm going to, if I start to multiply this out, I'm going to get x to the n plus, now here's where I get a little hand waving, a number. What are these numbers, right? One of those numbers, whatever level I'm at, yes? But it's just a number, right? Times x to the n minus 1 h. Is that cool? 1 less x, 1 more h. Just like we did here. All x's, 1 less x, 1 more h. 1 less x, 1 more h. 1 less x, 1 more h. No. You guys semi with me? If I were to do this, it would start off like this, plus a number times this, plus, I can be a little more specific. Let's be a little more specific here. This will help us out. Second row, what's the second coefficient? 2. Third row, what's the second coefficient?
3.
Fourth row, 4. Nth row, no, come on. Second row, 2. Third row, 3. Fourth row, 4. Nth row, n. So I'm going to have n of these. Some number, plus some number, times 1 less x, 1 more h. Yes?
Would that be also n?
No, definitely not.
Right.
Yeah, we have, you can tell from the example here, the third number in is going to be something else. I really want you guys semi with me. And then the rest of this is going to be some number times some number of x's times at least 1 h, right? H to the 3 plus whatever. It's going to keep going up in h's. Okay, really? Why do I not have to be specific here? You'll see in a minute. Okay. And it's over h, yes? Oh, and I forgot. Then we have this at the very end, right? X to the n minus x to the n is at the very end. All right, so then these cancel, die. Right? Did I leave? No, I didn't. Thank God. And then an h cancels here, right? And then 1 h cancels, so I'm going to have n x to the n minus 1 plus number x to the n minus 2 h plus a bunch of shit with h's. And why does that all have to know? Because I'm letting h go to 0. So the only thing over there that doesn't go to 0 is that guy, right? If I let h go to 0, he goes to 0. And all of these go to freaking 0 because they all have at least 1 h. That's why I didn't have to be that specific. So what have we just proved? We just proved that f prime is n times x to the n minus 1. So what's the rule? That comes down, and the power goes down by 1. Polynomials are nice, period. They're just nice. So their derivatives are nice. Okay, let's see if we really understand what just happened. Are you ever going to have to do this yourself? No. I might do a bonus problem kind of related to this, but you're never going to have to kind of do all this yourself. I do want to say one thing, I think. Let's see. Do I? Maybe. There is one thing that comes out, I'm not gonna teach you combinations and stuff, but I do wanna talk about one, little notation that comes out of discussing combinations. Am I speaking, I think I'm speaking English. There's a interesting little thing like that. Has anyone ever seen that mathematical symbol? So this is not 4! Right. What is that? Does anyone know what that means?
Factorial.
Factorial? And what does that mean, tell me to do? What does that tell me to do? So here's what this is defined to be.
4 times 3 times 2 times 1.
Yeah. So 80 factorial would be 80 times 79 times 78 times 77. Good Lord. All right, so now I'm going to tell you one thing. If I had 7 people and I needed to choose 4 of them, right, does everybody understand? I have 1, 2, 3, 4, 5, 6, 7. All right, I'm leaving you out, sorry. 7 people. And I wanted to choose 4 of you. How many ways could I do that? Right? Stay with me now. How many people could I choose to go in the first spot?
4.
No.
Oh wait, 7?
How many people am I choosing from?
7.
So how many people could be in the first spot?
7.
7. Now how many people could be in the second spot?
6.
6.
5.
So that's why factorials, when you're talking about choosing stuff, do you see how this is, now this is interesting because this is like, let me see if you guys are cool with this. This is like 7 factorial, but it's missing something, correct? What should be back here if it really was 7 factorial?
3
And what is 3 times 2 times 1?
3 factorial?
6.
Oh. Yeah.
I like the 6, but it's 3 factorial, right? Okay. All right. Anyway, so again, I'm not going to teach you all the combinations, but factorial will show up again. And I just wanted to kind of show you why factorials show up with Pascal's trying. Yes?
Why is that minus 3 factorial?
Because it's multiplication.
Yeah, the only way you can kill multiplication is divide.
Wow.
Yeah. I like it. All right, so this is all semi-unnecessary. Oh, red, you come right up with it. I'm going to use red. Can everybody see the red okay? Okay, it's the only one that wants to erase fully. Okay, so now we know this rule. Rule number 1. Shortcut rule number 1. If f of x equals x to the n, f prime of x equals n times x to the n minus 1. So let's try a couple things. Let's make a rule number 2. What if f of x is a constant? So letter C is a constant. Like f of x is 7. What does derivative mean again?
The slope?
What does f of x equals 7 look like?
A line?
Flat line.
Flat line, so what would its derivative be?
0.
0. And let me see. Right? If you plot y equals 7, or any number you want to, it's flat line, therefore its slope is 0, therefore its derivative is 0. How does that match up with this rule though?
There's no power to it?
See?
Oh, the power goes down, so it's going to be 0.
Because what is the power currently? Is there an x here? How many x's how many x's do you see here?
None.
So this is x to the 0, yes. What is x to the 0?
1.
1. So if I apply the rule, what happens? 0 comes down, multiplies, and then it doesn't matter. It's killed it, yes? So it still follows the rule. But you don't even have to think about the rule. It's easy. The first, if I had, is this really another rule? Not really. If I had f of x equals mx plus b, what is f prime?
M.
What?
MX. MX plus B?
It's m,
Ah.
right? What happens? So this is the first power, yes? So doesn't the one, and actually, let me say it like this first. What is that the equation of?
A line.
A line. And what is this asking me for?
The slope of
The
the
slope.
line.
And what's the slope of mx plus b?
M.
M, by definition, right? Now how does that line up with the rule? Well, that's the first power right now, right? So it comes down, 1 times this, right? X to the 1 minus 1, And b is a constant. We already know that goes to 0, yes? And therefore, I get m. So it's got to, since derivative is just slope, it has to match up with what we did before. Otherwise, we got to throw it all out. Okay, I like it. Now, I did something here. I know the slope of mx plus b is m. Therefore, the derivative must be m. But notice that this is the first time we're kind of officially talking about the sum of two pieces. And well, how does it seem like, so for example, oh, you're erasing now too, that's neat. Okay, just had to prime the board, I guess.
It's kind of erasing.
Well, compared to earlier, it's doing it much better. So example, what if I had f of x equals x to the fourth minus 2x squared plus 3x. What would f prime be?
4x cubed minus 4x.
Good, so the 4 comes down, the power goes down by 1. The 2 comes down,
And plus 3.
and the power goes down by 1. And then here, 3x is just, the slope is 3, I know that. Just see the slope is 3. What's this?
12x squared minus 4.
Do you see how the idea didn't change? F prime is just a new function, and if I take the derivative of a function, a polynomial especially, I know what the shit to do. Doesn't matter that it's a second derivative. All right, where am I? Okay. I do want to take a second and actually prove something we just did. Yeah, let's prove what we did after we did it. That sounds about right. Let me see if you guys can handle this. Let me define h of x to be this. So h of x is the sum of two functions. And I want to figure out what h prime of x is. So unfortunately, while we are learning shortcuts, we still have to go back to limit definition when we encounter something we don't know the shortcut for. We got to use the limit definition to figure out a shortcut. So this is asking me for h prime. Oh, let me do this. I did this on my notes, and then can we just make this, let's make this capital M. You guys understand why? Because h is going to mean its own thing here in a second, yes? You understand? Okay, okay. So this is the limit definition. Everybody see now why I can't call it h of x? Okay. What is m of x plus h? What is this? Here's m of x. So what is this?
Oh, fx plus g. Or
Oh, plus G of X plus H.
Is that cool? M of x is f plus g, so m of x plus h is f of x plus h plus g of x plus h. So what is mx? It's this.
Yeah.
And this is one of the biggest mistakes I see. I've got to subtract this function. So I got to put in parentheses, so I subtract the whole function, not just the first bit of it. So see how, let's see, all over h. Now watch this. This kind of thing's going to happen later, and this is a really nice baby step into this. Can anybody see f prime up there? F prime is hidden up there. F prime would be f of x plus h minus f of x over h. Do you guys see it? Here's f of x plus h, right? There's minus f of x. And then can't I separate those and put them over h plus g of x plus h minus g of x over h? Right? You guys see that? Maybe. Aren't they all over h? Can't I break them up to still be over h? And then, all right, let me do this. This limit here is given what symbol? What is that the definition of?
F prime?
F prime. And of course, that's the definition of G prime. So we just proved that if I have a sum of functions, it's the sum of the derivatives. That kicks so much ass. It's almost like, let's see if you guys are cool with this word, the derivative operator, the derivative process is linear. It can distribute. So if I have the derivative of a bunch of things adding or subtracting, I can just do the derivative of each piece adding and subtracting. Sort of like I'm distributing a 2 or something. Okay. Oh yeah, I was going to do that. Nah, it's a little freaky. Let's see. Yeah, okay. Maybe I won't do this. Yeah, let's do this. What do you guys think about, so the rule again we just came up with a minute ago is, if I have this,
Oh.
no, you're fine. It's not your job. Then I have this. Here's the question I have for you. What end does that work for? What ends? Definitely, so far we know it works with like 0, 1, 2, 3 and up, right? So what about fractions or negatives? Does it work?
Probably.
Yeah.
Why should it?
If it works for numbers less than or more than fractions, then it should work with the fractions.
Not necessarily, no. But thankfully, it does. So real quick. Let me see if you got, oh boy. And again, I'm going to show you something. Something you might never need to do yourself. So even if you don't even want to copy this down, I understand. How can I rewrite this? X to the
1/3.
X 1/3. All right. So of course fractional powers are just roots. Right? So what would F prime be? It would be the cube root of X plus H. Now. Okay. Oh jeez.
It would be
Stay with me now. Remember, this is something you're supposed to be able to do right now on your own. No, hell no. This is something I'm going to expect you to be able to do on your own.
Eventually?
No.
Oh.
Can I take a guess?
We're going to do this together. Guess for what?
But
Well, no. I'm going to prove that this works for it. So we already know what the answer is supposed to be. So you can tell me the answer is supposed to be using this, but I want to show concretely that it actually works. Can somebody tell me, if this is X to the 1/3, what answer should we get here?
1/3.
1/3?
1/3 X to the
Negative 2/3. I love it. Okay. So I know if that's supposed to work, I better get that answer from this process here, yes? Because this is the basic definition of derivative. But how the shit do I do this? I can't multiply by the conjugate. That's not good enough. Because this is a cube root. And if you don't believe me, oh, some of you guys have turned off. Stay with me. You never have to do this. You don't even have to copy it down again. But at least pay attention. Okay. You can't just do this. Can anybody see why this won't work?
Oh,
Like,
it's a
multiply
cube.
them together, it won't cancel out.
Yeah, when you multiply this by this, you get cube root of something squared. Shit. So that's why square roots work, because square root times square root is square root of something squared. Okay. Stay with me now. Stay with me. Oh no. All right. Can somebody help me? A little side note again. What is all right? You already forgot what it was going to be, right, Jeff? You totally just did. It's just out of your head. Oh yeah, there it is. What? How do you factor a cubed minus b cubed? Remember, this is Pulp Fiction kind of stuff. No? Yes.
A minus
Yes, one of each. And because it's a third power, And can you tell me really quickly? Can you tell me? Isn't that the cube root of this? Isn't that the cube root of this? Okay. And then what goes here?
A squared.
Got it. The other two a's. At the end goes the other two b's, right? Good. Yes.
Plus A.
Plus
2
ab.
A.
Yes.
Plus.
Now. Now. Yes. Let's see if you guys understand this. I'm just going to write this. That's the same thing. That's the same thing. What does it say? Take the cube root of this and put it there. Okay, take the cube root of this and put it there. Put two more of them over there. Okay, put two more of them over there. And the middle is this times this. Do you guys see that? That's the extension to that we don't often realize we can do, because this is more powerful than it looks. It says anything that looks like this can be written like this. Does that look like this? Yeah, it does. Right? Isn't this something cubed? It's cube root of a cubed, isn't it? Okay, so what does that do for us up here? Well, isn't this like this piece? What's a? X plus h. And what's b? So if I multiply this by this, so that would be the cube root of x plus h squared. See how I'm going to get 3 of them now? And again, don't try to fully you can sit and watch, right? Again, this is weird shit. I would be really, really surprised if anybody came up with this on their own. And I'm not saying it's impossible, I'm saying it's weird as shit. You don't even know you're allowed to do this kind of shit. Yeah, and then the middle term is going to be cube root of x times x plus h. And as always, Jeff, is it you that sucks? I think it's them that suck. Okay. I don't give myself enough room. Yeah. Okay. Plus cube root of x squared. And then we multiply the bottom by the same thing. Blah, blah, blah. Same, right? I don't care. You don't have to copy this down, so I don't have to write anything. What happens on the top? Cube root of, what happens here? Doesn't this just become a whole a minus a whole b? So I've set this up so it's going to become a whole x plus h. And you can see that right here, yes? 1/3 of an x plus h times 2/3 of an x plus h is a freaking whole x plus h. All the shit in the middle cancels. That's what this guarantees me. And then I get a whole one of these. Are you guys still with me a little bit?
Yeah.
This is trippy. I've never actually, to be really, really honest, I've never done this in front of a class. This is neat. I never thought to try to do this to show you. And you're all like, we would have been cool if you never did. But too bad. So x is canceled. The h is canceled, yes. So I'm left with the 1 up there. And I got the limit. Don't forget my limit. What happens down here? Let me go ahead and apply the limit. What happens down here if I let h go to 0? Don't I get cube root of x squared? Cube root of x squared, yes, because the h is 0. Cube root of f, Jeff. That's better. It's supposed to be a 2 up there, right? It's supposed to be b squared, right? Okay. So don't I get 1, 2, 3 cube roots of x squared? Well, what is that? Isn't that 1/3 x to the negative 2/3? Which is exactly what it should be if that rule works for fractions. So we could do something kind of similar for negative powers. I'm not going to make you go through that. Okay. So that works no matter what the hell n is. It works for all real numbers. Even irrational powers. Okay. All right. I don't know if anybody's trying to copy that. Are you guys good? You good?
Yeah.
Okay. So help me out here. What if f of x, how much time do we have? let's see, cube root of y squared minus 1 over y to the 7th. What would the derivative? Now, what I would highly recommend you do, what's the rule, the only derivative rule we really know yet? What form is it supposed to be in? The derivative of what equals what? It's the only rule we know. Derivative of x to the n, right? Remember? What were we just doing? Derivative of x to the n is n times x to the n minus 1. Is either one of those in that form? Not currently, no. So before we figure out this, let's rewrite this. And do you see how some of you guys rewrite this, but you put a prime here, and then you think you've done the derivative. You guys see that? I'm not about to do the derivative. I'm just going to rewrite this. So I'm not going to call it f prime yet. So how do I rewrite this?
Y to the 2/3.
Minus y to the
Yeah. Negative power means flip, right? Now I can attack it with derivatives. Let's see. Oh, that will try to get high, but I can't. What's that?
2/3.
Yeah, the 2/3 comes down. All right, this is going to seem silly right now. Here's a little shortcut. Watch. You can use it whenever you take derivatives of fractional powers. What is 2 minus 3?
-1.
See, 2 minus 3. -1, put it back over 3. So when you're doing the derivative of y to the 49 over 53, right, something like that, that's how you do it really quickly. Yes. I'm not done yet though, right?
I was gonna say the next part.
Yes.
Would it be a plus?
Good. -7 comes down, times the negative is plus.
Plus y to the 7, the
-8, good. So another really easy thing to make a mistake on is put -6, because your brain says 6 is less than 7, but -6 is more than -7. That ain't going good. You got to go down by 1. Is that cool? Not too bad, right? Relatively straightforward. Okay. Well, let's find out. I like it. I think we could do all. Yeah, we can do all these. Good. Don't worry about the. Well, should I do that? No, I'll do it in a minute. Don't worry about the sign derivative. We're going to do that in a minute. Sure. Oh, let me get one more. All right. So I kind of re-go over. Oh, and there is one thing on here that I'm so happy. I always forget this. You'll see at the top. Did I put it on here? Yes. So this notation with the prime, you'll see at the top, that's Lagrange's notation. And that's how you pronounce Joseph Louis Lagrange, right? Or if you want to Americanize it, Lagrange. This notation, so another way to say the same thing is like that. The power of this notation, you won't see it until you get to multivariable stuff. Because you see how this tells me this is the derivative of this with respect to x. So if I had a function with more than one variable, somebody has to tell me with respect to which variable. This notation is not as useful immediately, but we do have to lay the foundation that it exists. And this is Leibniz's notation. Gottfried, I love Gottfried. Okay, good old Leibniz. So just wanted to throw that out. This is just another way to write the prime. And you can also write it like this, right? That's acceptable. And do you see how that's kind of nice? This notation is kind of nice because it reminds you it's a rate of change, right? How much the function changes with the change in x. So if I had, for example, a position derivative, that would be change in position with respect to time, yes? So this notation actually helps with remembering what the hell the units on something are. Because then you can say, position's feet or whatever, and time is seconds. You can see it. This doesn't help you out with that at all. It may. So what I want you guys to do, can you see the examples at the bottom? I want you to try those out. Geez, Jack, yeah, give yourself some room, buddy. All right, we'll do the rest in a minute. Do you have a question? Okay. That's the actual grade and your overall average. So what? Isaac, there you go. This is your overall average right now, and you curve the grades. That's your test. Did you get a worksheet? I'm sorry. All right. I get the worksheet. I just copy it for the worksheet. Let me get it.
The letter grade, is that after the curve or before the curve?
After. These should be pretty quick, right? These should be. The other two might take a little while. Okay, I'm gonna go ahead and start catching up to you.
Like 2 and 3?
So again, sorry?
2 and 3 on paper?
Yeah, dude. Huh?
I thought, okay, I was talking about 2 and 3 on paper or those last two.
Oh, the 2 and 3 in the paper.
Oh, yeah.
All of these should be pretty straightforward. Alright, so what's this first dude here?
5x to the x is 1.
Taking the acid. And then of course this guy,
Negative 33 to x to 10.
crazy shit. And again, right here, if I put a 3 here, what would that mean? Put a 3 in here and I get a number. What would that number mean?
The slope.
Slope at
X.
of
Negative 3x.
f of x. Oh yeah, of the function. Yeah, you got it. So the slope of this function at 3 would be whatever number I get when I plug a 3 in there. And it would be, can you understand that would be stupid big? Because you freaking x to the 11th, it's going to go crazy. Yeah. Okay, maybe. This guy, really easy.
16x to the 7.
Bang.
Oh, shit.
Did I give you, what did I give you? Okay. Did I give away my, I might have given, no, I didn't, okay, sorry. I had one of these with some notes in the back. This guy, same way. The only thing you have to be careful about, one thing you gotta be careful about.
The
Negative
negatives.
16x to negative 2.
See, that's what you gotta be careful.
Negative 4, I mean.
There we go. Our brains go, wait, 4 is bigger, but it's negative, so negative 4 is small.
But the worst part is I actually wrote that down, and then the more you talk about it, the more I thought about that.
Oh, shit.
I wrote.
Here's another way. Watch it real quick. Let me show you something, a little bit of something. The shortcut here is 2 minus 5. Well, the 2/5 comes down, right?
It's a 3.
That's a third.
Where am I at?
It's a 3. Number E, there's 2.
Oh, is it a 3?
2/3.
Okay, my bad. So the 2/3 comes down. And then the power becomes 2 minus 3 over 3, right? Because, and why does that work? Because I would subtract 1, which is 3 over 3, so I'm going to subtract 3 from 2, and that's always going to work that way. So watch up here, real quick. This might be kind of silly, but I don't care. What's negative 3? See, isn't negative 3 over 1? What's negative 3 minus 1? Because I subtract them, don't I? Negative 3 minus 1 is negative 4. Okay. But it's, what do I have to do with this one? Now watch this. Watch this. Do not write this. Error. Right? Do not write what I'm about to write. I always get somebody that tells me this is. That is so wrong. So wrong. Yes? It is so wrong because it's ignoring the root entirely. So this is not x to the 9th. There's no x to the 9th in there anywhere. There's a what now? There's an x to the 9
X to the 9
sevenths. Now I got it in a form for which I have a rule. What is it?
9 sevenths x to the power 2 over 7.
Yeah. So 9 sevenths comes down. 9 minus 7 is 2, and I put it back over 7. What do you guys think about, compared to some of the stuff we've done in here before today? How do you guys feel about this idea? Right? Some of you guys are like, it's about damn time. Alright, gotta turn the guy around. So go ahead and try number 2. I don't know if anybody's tried number 2 yet.
Was f(x) over a sloper?
So again, sorry.
Number 2 is f(x) over a sloper. Or either one of them.
So I want the tangent line to that function at that point. So to be really honest, oh, here's a weird answer. It doesn't matter if that's a slope of something or not. It's a function. What do I need to figure out about that function to get the tangent line? I need to figure out the slope, oh shit, of that function, right? So it really doesn't matter what that function represents. To get the slope, I got to take a derivative of it. I really want that to make sense. This is a 2-step problem. First step is like these guys. I already forgot what it was. Here it is. And by the way, did I just make up the number 47? Did I just make it up? What's got to be true if I'm saying this point exists on this function? When I plug a 2 in,
It's gonna
I
spin.
better get 47. Do I? I'm worried now. I think so. 2 to the 4th is 16. Times 3 is 48. Minus 2 over 2 is 1, so minus 1 is 47. Yay. You guys, that's where that point came from, right? It's a point that exists on the graph of the function. So I've got a point, check. I need the slope. So of course, what do I do to figure out the slope?
Derivative.
Take a derivative. And you see I put it in the right form. Now everything is in the form of a rule that I know.
Log x to the 3 plus 2x to the negative 2.
Good. Now, what am I going to plug into that? Please, dear God. Dear God. Dear God. It would be a really crazy problem if you put this whole thing there. So 99.999999934. of the time, you will not just plug this there. That's insane. You need a number there, right? I want a line, so the slope has got to be a number. So what am I gonna, how do I figure out what m is?
Plug in 2.
Plug in 2, because that's where everything's happening, right? The slope of the function at 2 is whatever the hell this is. Oh, this is gross, isn't it?
It's 96.
Why did I pick this weird shit?
96.5.
Okay, so, what is it, 96, oh, wait, that's not as bad as I thought. 1/4, okay, times 2 is 1/2, so 90 something, not too bad, okay. For a minute I thought it was really bad. And again, you could solve for B, you could use this, whatever method you like. I kind of try to use this when I'm lecturing because this is going to come up later this semester in a different form. So I really kind of want this in your head. So do y minus the y piece equals m times x minus the x piece. So y equals 96.5x. 96.5 times 2
193.
193 plus 47, right? 96.5x minus 146. I don't know. Does that sound good? Anybody know a quick way to check to make sure that at least makes sense on some level? If I put a 2 in, what should I get? 47. And sure enough, you get to do it. So what this means is, if I graph this function and I graph this function, this will touch that one perfectly right at that point. That's exactly the direction something would fly off in if it came off the rails at that point. Crazy shit. We've done a problem like this before, right? Okay, so that's going to keep coming up. I like number 3. Go ahead and try number 3 if you haven't tried that yet. Everybody should have them. Where's Tyler? Hey.
Current overall average, curve the grade width, there's a few testers, the corrections.
Do the data.
Gabriella,
Hey.
same stuff, so overall average, curve grade, the test is there, you can make corrections.
You go. You go. You go. Has to be 2, 4, 6, 8, 10, 14. Wait, 2, 4, 6, 8, 10, 14, 16, 17. So no Miguel, though, right? Okay. That's pretty.
Back.
Yes, Ricardo.
Yeah, when you say overall average, you mean like our class grade or are you saying class average?
Oh, that's your overall average. That is your, not the class average. Right, the one in black, the grade in black up by show work, that is your current average.
For the test or for the whole class?
Oh, I see. It's not including homework, because they don't put homework in until the end. Because you have all the time in the world to make corrections and all that kind of stuff. So that's basically the average of the test and the quizzes. Yeah. So what does it mean when your teacher tries to write with the markers that open? What does it mean for something to be a horizontal tangent line? tangent line slope will always be constant, but I heard the right answer over there. If it's horizontal, that means that's where it's 0, right? Isn't that when we were trying to graph f prime given f, we first figured out where it got to the top of the mountain? Because that's where it's flat, that's where it's 0 at that moment, right? If I throw a pen in the air, isn't it, how fast is it going right at the top? 0. Its velocity is 0 there because it stopped going up and it hasn't started coming down yet. So I need to figure out the derivative and then set that equal to 0, because we just said to find where its tangent lines are horizontal, I find where the slopes are 0. So I find where this derivative is 0. What's the derivative?
3x squared plus 12x.
And I want this to be 0. For those of you who immediately start doing quadratic formula, stop it. Stop. Especially with all these funky big ass numbers. What should you do very first thing?
Take
Take out the 3. Take that. Yeah, I can kill the 3. Right? You just kill the 3. 0 is going to eat the 3. Here we go. So get x squared plus 4x minus 21 equals 0. That looks really, really nice. Yes? Plus 7 minus 3. So I get x equals
Negative 7.
-7. 3, right? So at these x values, this function would have a horizontal tangent line. You can go one step further because it wasn't specific. At what points? -7, comma, plug a -7 in, and 3, comma, plug a 3 in. I really don't care. You just plug them in the calculator, who cares? Right? That's not interesting. Yes?
So you know how it says to find the local axis? So do we just take the derivative to find what that equals 0?
So what I meant by that is, that's kind of getting us ready for the next thing, the next big thing we're going to do after we do some more derivative rules is, okay. All right. So where's the slope 0? Well, the slope is 0 there. And that is that a max or a min? Max. So it's going up and then it's going down. That's a max. Here, of course, is a min, going down and then going up. Here it's another local, right? Because this is taller than that, but locally, are you ready for this? In a neighborhood, this is the actual language. This is the math language. In a neighborhood around that point, that is the highest point. Okay. And what about, Jeff, what did you just do, buddy? You did not do what you wanted to do. Sorry, everybody. All right. What's the slope here? 0, but is that a max or a min? No. I kind of did a little too extreme there. For just a moment, it is 0 right there. It's a z. It's like it says, I'm going to turn. No, I'm not, huh? It's like a cubit, right? So that is not a max or a min. But it seems like if the derivative equals 0 somewhere, that could be a maximum or a minimum. But it doesn't have to be, because it could just be resting for a second. Because here the slope is negative, and here the slope is still negative, so it didn't turn. Okay, so that's going to be in our future. We're going to do a lot more deeper analysis than this on slopes. We shouldn't be surprised. Okay, this is good. Actually, why don't we leave early? Because I got a meeting that I'm going to join late anyway. Might as well join it less late. I'll talk about this. You can look at this sine dude. I think we did this before, if I'm not mistaken. I feel like I did that. You guys like, we don't know. All right. So we'll talk about it again next time, but that is it. Come on up if you have any questions about anything. Otherwise, I'll see you Wednesday.